So at this point, we've done 3 out of the 4 transformations. We've done all of them except for the shear. So the shear is going to be new. It's probably not something you've seen in geometry. So before I get into the actual matrix mechanics of how this works, I want to talk about what a shear might represent. So one of the kind of go-to examples, I mean, you could look up what is a shear transformation if you want. I'm going to kind of go off of the first example that I think of, and this has to do with fluid dynamics. So if you have some sort of liquid in between two surfaces, so for example, let's say I have a fixed surface here. So I don't know what that is, but it's some sort of fixed surface. And then I have another surface up above. Maybe this is moving with some velocity this way. And let's say there's some sort of fluid in between there. Now, the fluid that's really close to this plate up here is going to kind of move with that. It's going to move this way. If the water, I'll just call it water, but if the water is over here, it's also going to move this way, but probably not quite as far. And the closer we get to this fixed surface, the less it's going to move. But it is going to create kind of this eddy in the water if we're moving this other surface in the direction of the velocity. So what we can think of then is if I have sort of my xy plane fixed here, then we would say that the y values are all staying the same. So notice these y values are fixed. And the x values are all getting shifted to the right. So the x values are shifting. And the shift actually depends on how far we are in the y direction. So the shift actually depends on y. So what we're going to do now is, what we would say is we could define a shear, which is, so this would be a shear parallel to the x-axis. By some factor which we could call k times the y coordinate. So the shear, first of all, is parallel to the x-axis. There's some factor k that is being multiplied by the y coordinate, and that tells us how much we're shearing depending on where we are on that y. So this is how you might apply it. I'm going to now just show you what the actual matrix transformation looks like. So if we were to do exactly what I said there, this shear that is parallel to x-axis by k times the y. Then the matrix we would be using is going to look probably somewhat similar. We're going to have ones on the diagonal. And then I'm going to go ahead and put a k right there. And then this will just be a 0. So if I were to multiply this, so this would be my transformation matrix. If I were to now multiply this by some general xy, let's see what would happen if I did I'll do the actual matrix. If I did 1k and then 0, 1 times just some point xy, notice that my x value is going to be x plus some multiple of y. Again, depending on where I am on my y-axis, this will maybe be a larger or smaller amount. And then the bottom part's going to be y. So y actually remains unchanged, just like we said in this example. The y values are fixed, and the x values shift depending on the value of y. If we wanted to go the other direction, so this was the first one, if we wanted to be parallel to the y-axis and multiplied by k times the x-coordinate, then we would have 1, 1 again, except now this part would be 0 and this one would be k. So those are examples of shears. So let's do a quick example. I've already sort of done an example up there, but we'll do another one just to give you an extra sense of what this looks like. So let's say, let's write the matrix that is a shear parallel to the y-axis and I'll say by a factor 3.5 times the x coordinate. Oh, of a certain point of the point. Let's go back to the one we've been using, 3, 2. So first of all, we're going to write the matrix, and then we're actually going to do the transformation. So the matrix is just, let's take a look at where 0 goes and where the k goes. So we're parallel to the y-axis, so we're in the second situation. So that means it's going to be 0 and then 3.5 times the vector 3, 2. And so then my new point is going to be at 3. Now I have to multiply 3 times 3.5 and then add 2. So I said 3 times 3.5 and then plus 2. So that'll be 10.5 plus 2, so it should be at 12.5. So if we were to visualize this, we could go ahead and graph our point 3, 2. And then on the y-axis, I'm going to have to get all the way up to 12.5. So what happens is this point that was originally sort of this one is now going to go up to here. And that's how a shear would work. So now we've done all the transformations. What I want to do next to kind of finish this section off is a typical problem you'll see in Delta Math. So what we're going to do is a couple different things. The first part is we're going to determine a transformation matrix that reflects over the y-axis and dilates the y-coordinate by a factor of 5. So this is going to be sort of part A, and then part B is then write the effect this matrix would have on a general point x, y. So for part A, we're just coming up with the transformation matrix. You might want to take a look at your previous notes, but recall that the reflection across the y-axis means my x has to change to negative x. So I'm going to put that there, -1 and then 0, so that when I multiply by my x coordinate, it'll just be negative x. And then I also want to dilate the y coordinate by a factor of 5. So I'm just going to do this to it. So notice that -1 is going to flip the x if you look back at our reflections, and then the dilation of y will be handled by that 0, 5 in that second row. So that's all we had to do for the first part. Now in the second part, we're just going to take t and multiply that by xy. And when I do that, I get -x and then 5y. And so then my final answer would just be that right there, which looks correct to me because the -x is going to be a reflection. And since it's changing the x value, it's going to reflect over the y-axis. And then that 5y is just going to multiply any y values, so that will in fact be a dilation, or a stretch in this case, by 5 in the y direction. Oops, by 5 in the y direction. All right, so now you've seen all the different transformations, and you've seen what the matrices look like. You should be able to come up with those. We're going to have one more video that's going to deal with a slightly different situation.